All right, take your protractor. We're going to talk about 4.6 section today. We've been talking about triangles for quite a few weeks now. We're still kind of talking about triangles, but we're going to shift to what we call similarity here for a little bit. I want you to take your protractor and we're going to draw two right triangles. Now you should watch how I do the first one, and then you can apply that. You're first going to want to get a dot, two dots on your paper. So down here near the writing, you're going to make a dot over near the left side, and then you're going to make this, another dot down near your writing again, about in the middle of your paper. You're going to construct the two right triangles. That's going to be where the right angle goes, where those dots are. Take your protractor and set it, the center point, right on that dot. And use your pencil now and make a dot at the 90 and keep your protractor right where it is and make a dot at the 0. So you're going to make a dot where the 90 is, you're going to make a dot where the 0 is. And if you connect those three dots or whatever, those two dots that you have, if you connect your original dot from the dot that you made at 90, you're going to end up going straight up. And if you connect the original dot that you made with your dot at 0, you're going to go straight across, which should give you an exact 90-degree angle. And then you can even use your protractor again to verify that you have your 90-degree angle. So if you look at your protractor, you should see the exact 90 degrees. Now up here it tells us what we want to make the two legs. One leg is 3 centimeters, the other one is 5 centimeters. So I'm going to make the leg going up the 3 centimeters. Now I don't have a ruler on the bottom of my protractor, so I need to get out a ruler, but you should have a ruler on your protractor at the bottom. And I'm gonna make the line that's going across, I'm gonna make that my 5 centimeter line. I'm gonna put that right at 5 centimeters. Then I'm gonna swing it up to the top line, and I'm gonna make that top line my 3 centimeter line. So you're just going to have to erase down to where the 3 and the 5 centimeters would go. So I would make the dots on the lines that you made and then just erase the extra part. Erase the part that's extra so that way you have, see, that's a little bit too much. That way you have a 3 centimeter and a 5 centimeter line, and then connect that into a right triangle. Connect that into a right triangle. And then let's label everything. This one's 3 centimeters. This side is 5 centimeters. And we have a right angle, so we could actually make our little box that shows right angle. So that's just everything labeled for us. Okay, so that's what you'll have on the first one. 3 centimeters, 5 centimeters. You got your little box. You've already proved that's a right angle. You checked it with your protractor. You erased the extra part to get it to 3 and 5 centimeters. And then you connected it. Now you can do the same exact thing on the next dot. This time make it 6 and 10. Okay, make it 6 and 10. So do the same steps. Put your protractor again, measure where 0 and 90 would be, and then make those dots at 0 and 90. As long as you measure at 0 and 90, it doesn't matter if it's a diagonal, going whatever way you want it to. As long as you measure 0 and 90, you'll have a 90-degree angle. So you make your dots, and then you draw in your two lines. So that'll give you your 90-degree angle, and then you're going to make them 6 and 10. So Make it as accurately as you can. Now, it might go up into the writing a little bit. That's okay. Or if you go to the side a little bit, that's fine. Just make sure you get the triangle on your paper. Somewhere on your paper. I need to recheck my top measurements. Make sure it is really a 6. Something's telling me it might not have been just right. Nope, it's good. All right, so connect those to make your second right triangle. All right, so I'm going to label that as 6 centimeters, and then 10 centimeters, and then we'll have our little box to make sure it's a right angle. Okay, so far we've got 2 triangles. Now, I want to talk to you a little bit about what we have been doing over the last week or two. The last week or two, we were talking about letters. We had some of them that had 3 letters, A, S, A, S, 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 A, S, and then we had the 2-letter one, which was HL. Right, so we've been talking about letters. Why did we need those letters? Okay, the key word there. You just said it. Prove. Prove what? That the triangles were congruent. Okay, that's the reason we use them. It wasn't just because they look cool. You know, ASA looks cool and SSS looks cool. Yeah, they actually have a purpose. They are proving that the triangles are the same, congruent. One would be on top of the other. These are not congruent. The 2 that you just drew would not fit perfectly on top of each other. Okay, they are not congruent, but we do have another word that we call them, which is you see at the top of the page, similar. We're talking about similar. Okay, but let's test and really see how similar works and what it looks like if they are similar. So the next thing we want to do is right here. It says it, measure the 2 acute angles in each of the right triangles and round to the nearest tenth. Well, we can just round it to the nearest angle. And then what do we notice? So let's do that next. Get your protractor out again and measure the acute angles. Yours should probably be pretty close to mine. If I can get my protractor on there correctly. Mine should be right about 31 degrees. What does your small one come out to be? Okay, should be about the same. So test yours and see if you get about 31. If you get 30, then you were a little off. Because a 30, 60, 90 triangle would not have exactly 3 and 5 as your sides. So, just telling you. You should take a look at it. And this one should be, and if you look at mine, right there, it looks right on the money at 59 degrees. What should the 2 acute angles add up to in a right triangle? They should add up to 90. But I thought angles in a triangle added up to 180, though. Why do the 2 acute angles only add up to 90? Because I already got a 90 with it, right? So the 90 and the 90 together would make my 180. So yeah, make sure the 2 acute angles that you just measured are going to add up to 90 degrees. Because plus the other 90 will give you your 180. Now measure them in the big triangle. Measure them in the big triangle. What are you predicting is going to happen here? Do you predict they're going to be the same measure as the small one, or are they going to be double because the sides are double, or what do you think? Oh, hold on. They should be the same. I had a page for you to use for Scratch. It's got all the questions on it, so if you need to write them. Sorry about that. Okay, so they should be the same. Because you still need to have two acute angles add up to 90, right? Still a right triangle. So let's see how we did here. Well, it looks like my first one is at 59. It's my bigger angle. Let's go down to the other smaller angle now and see if that one's 31. And yep, it looks pretty good right there at 31 degrees for me. So 31 degrees again and 59 degrees. So what do we notice about the two angles in each of our triangles? Or actually, all three angles in each of our triangles. They're congruent. So you might want to put here next to what do you notice? Congruent angles. So what did we notice? We noticed that we have congruent angles in both triangles. We had congruent angles last time, didn't we? When we were trying to prove that two triangles were the same and we had ASA, we had two angles that were congruent and the side in the middle. So we had congruent triangle angles then, we have congruent angles now. Okay, measure the hypotenuse in each of the triangles. So I need a ruler. You should be able to use your protractor still because you should have a measurement on there. Measure the hypotenuse in each of our triangles. The hypotenuse is the longest leg, longest side. So for me, my hypotenuse there is 5.8 is my small one. 5.8. Make a prediction as to what you think the longer hypotenuse should be if the smaller one is 5.8. 5.8. What should the bigger one be? Should we double it? Triple it? Quadruple it? Double? Okay, so you're looking at 11.6 maybe? So let's see how close we get. Now, did yours come out to be 5.8 as well? Good. All right, should. And then you should double it, and yes, mine is 11.6, almost right on the nose. So hopefully yours is 11.6 as well. Oh. Sorry. My bad. Some of them go longer, I think, don't they? Some of them don't. Oh, that's just the inside ones that are 10. Huh? Sorry about that. You could also measure them in inches, and the two of them in inches should still be double. All right, so when we measured the two hypotenuses, what did you notice about all the sides? Okay, the doubled in the larger triangle. Right, all the sides are doubled in the larger triangle. So what can we call these two triangles? Similar triangles is right. Now we are going to talk about a similarity statement. Remember we had a congruency statement. We had triangle this, congruent to triangle this. Works the same with similar. Triangle this is similar to triangle this. Right? I don't have letters right now. We'll do that when we come back next Monday. But there is a symbol that we could use to show that these two are similar. Do you know what the symbol looks like? It's just a squiggly. No equal sign underneath it because they're not congruent. They're just similar. So you put the little squiggly between them. Those two triangles are called similar. You might even want to put the word similar above it so you know. So you know what that means, similar. That's what that little squiggly means. Okay, moving to the next one here. Okay, so we should now be able to come up with a definition for similar triangles. You just drew them. Similar triangles have blank sides and blank angles. Okay, and can't use the same word in the definition. Okay, congruent what? No, they don't have congruent sides. One had 3, one had 6. Proportional sides. Very good. Nice key word. Daniel said that. Proportional. What does proportional mean? We know they're similar, but proportional, the word proportional. What is a proportion in math? Two equal fractions. Hard to explain? Two equal fractions. You got two equal ratios, you could say. Okay, so that's what proportion means. So if you look back at this first picture, and you have 3 matching up with 6, right? 3 over 6, is that the same fraction as 5 over 10? Is that the same fraction as 5.8 over 11.6? Yes, they all have a 1 to 2 proportion that we could reduce to. It's called a scale factor, which we're going to talk about in a minute. So that's proportional. They all reduce to the same ratio. That's what proportional means. They all reduce to the same ratio. And blank angles, congruent angles, you're right. The angles are the same, but the sides are not the same. The sides are proportional. Similar basically means this. You take a small one and you just enlarge it, or you take a large one and you make it smaller, kind of like a dilation, right? You're going to make an enlargement, you can make a reduction. Those are similar. All dilations are similar. So we are going to go back and look at dilations again now and see how they make similar figures. They're always going to be the same. So let me show you what similar basically looks like. Here's a triangle. Let's make it not look equilateral. There's a triangle right there. If I wanted to make a similar triangle, I could use this little button down here and I could go like this, and those are similar because I didn't change any of the angles. All I did was I made them proportional sides. I could make it a lot bigger. Now I can only use this is the only one that really makes it bigger and smaller with proportional. Those are similar because all I'm doing is making the angles stay the same and making the sides change. So that's what similar means. The angles don't change, but the sides do. Now here's how you solve proportions. Just a quick note on solving proportions. You might remember how to do this, but you might have forgotten, so it's a quick memory reminder. You got a proportion, you can use the cross products. If you have A over B equals C over D, you can multiply A and D, and you can get, then that's going to equal the B and the C. The A and the D are called extremes. Think about the 4 letters. A, B, C, D. First was A, last was D. Those are extreme numbers, outsides. Means are the inside numbers. The means always equal the extremes. You can see up here. You do it here, 1 times 6 is 6, 2 times 3 is 6. So the means and the extremes will always equal when you multiply them. Now you don't have to write anything down. It's on your paper. Just take a look at it in case you forgot. Let's test it though. Let's see how it works. Here's an example number 1. If 3 out of 15 plants from a distributor were diseased. I used to work at a Home Depot-ish kind of place, but I used to work in the garden area. So we would get shipments from trucks full of plants. And they look at this whole little flat of plants, and there's 15 in there, and 3 of them have a disease. So 3 out of 15 would have a disease. If the whole shipment actually had 250 altogether, because they keep pulling out these flats, about how many can you expect to be diseased is what the question is. How would we set it up, though? Okay, 3 plants that are diseased out of 15 total plants. Could we actually reduce that to make it easier for us? We could reduce that to 1 over 5, right? It's going to be equal to a 1 to 5 ratio. So we could actually make the math a little easier on us and reduce it to a 1 to 5. That's called a scale factor. Reducing it as far as we can. So we could actually take that 1 over 5 and using that ratio and setting it equal to what? What would be my new ratio? X over 250. We want to see how many diseased would be over 250. The X would be the number of diseased, the 250 are the total plants. Multiply your diagonals. If I could get this little thing to highlight, there you go. Okay, so we're going to get 5x equals 250. And then you're going to get x equals 50 plants. So 50 plants they could expect to be diseased out of that whole shipment. So that's how proportions could work. That's how we could solve it. That's how we could reduce it to make it easier for us. Let's look at what Ivy did. Ivy spent $14 for gas, and she drove 350 miles on that $14 that she put in. But that's not her whole trip. Her whole trip is 875 miles. How much money is she going to end up needing to put in for gas for the whole trip? What proportion could I set up? What ratio could I set up first? $14 get me how far? 350 miles. So $14, let's put the dollars on top so we know where the dollars is, and this is 350 miles. Okay, that's one ratio that we could use. 14 over 350. That's going to be the same as what my new ratio. What's my new ratio? What am I looking for? Dollars or miles? Dollars. So that's going to be my X on top. I don't know how many dollars. I do know how many miles I want to drive, though. How many does she want to drive? 875 miles. Miles has to be on the bottom because miles was on the bottom in the other one. Got to keep your units in the same places. All right, now this one we could reduce 14 over 350. Is it really going to help us a lot, or are we going to need a calculator anyways? Probably going to need a calculator, so I would use a calculator. I'd grab the calculator out, I'd multiply x times 350 would give me 350x. If you multiply $14 times 875, you get 12,250. 12,250. And if you divide both sides by 350, you get x equals $35. Now let's see if that number actually makes sense. She spent $14. She went 350. She wants to go more than 350. So you better have more than $14 on there. 35 is more than 14. Think about it this way. What if she doubled her miles and went from 350 to 700? We would have taken the 14 and doubled it to 28. 875 is still more than that 700, so 35 is still more than 28. So yeah, we got a good answer. That answer is correct, $35. A scale factor. It's on your paper. It's not something you got to write down. I just want you to know what it really is. It is a reduced ratio. Reduced ratio of corresponding sides in similar figures. What was the scale factor in our very first two triangles that we drew? A 1 to 2 scale factor. Could I have said 2 to 1? Yeah, if I went from the big one to the small one, you would say 2 to 1 scale factor. If you go from the small one to the big one, it's a 1 to 2 scale factor. It's always reduced because 3 over 6 is not a reduced fraction. 3 over 6 would reduce to what? 1 over 2. So that's your scale factor, is the reduced part. I found a scale factor in this one right here. A 1 over 5 was my scale factor because I reduced to 3/15. Okay, let's look back at example 3 now. On a building plan blueprint, the scale is 2 inches to 5 feet. 2 inches to 5 feet. So that's going to be my first part there. I'm going to put 2 inches over 5 feet. Is that a scale factor? Or could I reduce that?
No, you can't.
Can't reduce it. So that is a scale factor. So we're going to use the 2 inches to 5 feet. Okay, we could change all that. Do we need to, though? Not if you're going to keep the same thing on top and bottom. Okay, let's see what he's got. He's got a blueprint. Now, blueprints are cool because they allow you to see a whole building on a small piece of paper. To where you couldn't do that in real life because a building wouldn't fit on a piece of paper. But a blueprint, what they do is they just like dilate it, reduce it down into a exact replica of the other one, but at a scale factor. So they're saying on here, 2 inches on the picture is for 5 feet in real life. So Rolando uses the scale drawing for installing the building's telephone wire. So he looks at the blueprint and he's measuring how far on the blueprint the cable needs to go in the building. On the blueprint it measures 18 inches. He wants to figure out how much cable he's going to need now in real life. So where's my X going to go? On the bottom, right, because it's 18 inches is going to stay on top with the 2 inches. So 18 inches is on the map. He wants to know how many feet would that be in real life. X feet. So that's what we got to solve. So we're going to multiply x times 2 and get 2x. 2x equals and 18 times 5 is 90. And then x, and when you divide by 2, x is going to equal 45 feet. Now, is that a reasonable answer? 45 feet is more than the 18 inches. So yes, 2 to 5 has got to be more than 18, so we got 45. 45 feet. Now let's go the other direction and say he measured 42 feet out in the building. Out in the building, he's measuring his 42 feet out there. How much should that have been on the map, on the blueprint? Well, what is my first ratio that we're going to always use for this in solving one of these? Always going to use the 2 to 5. So 2 inches to 5 feet. Same exact scale factor. Now, what is that going to equal for my next ratio? This time, the x has to go on top because I want to find inches this time. And I know that I've already got 42 feet. Now, how close is 42 to 45 feet? Very close. So guess what my answer is going to be pretty close to? What got the 45 feet? How many inches was 45 feet? 18. I'm going to have an answer probably pretty close to 18 because there's only 42 feet now, huh? So let's multiply. We get 5x equals 84. And then when you solve, divide by 5, you're going to get 16.8 inches. Is that pretty close to 18? Yeah, 1.2 away from 18. So yeah, it's pretty close. All right, so there is your 3 examples for proportions. Just wanted to practice on proportions a little bit, just to remind you of, what we can do with our proportions. All right, we good there? All right, moving on. Last 2 here. Here's another example. Back to our triangles. Which of the following pairs are similar? Okay, we've got 3 pairs of triangles here. We've got these first 2. We got the middle 2. Those aren't triangles. Those are actually parallelograms. And then we've got the last 2. Are the first 2 triangles similar? Why? Okay, the yes is right. They are definitely similar. We got to tell why. Angles are congruent. Good, because you've got one arc matching up to one arc. You got 2 arcs matching to 2 arcs. You got 3 arcs matching to 3 arcs. So angles are congruent. And what else has to happen in similar? The sides are proportional. Now, how do I know they're proportional? Okay, the scale factor is a 1 to 2 scale factor, or you could say it's a dilation of 2, right? It made it twice as big. Technically not a dilation because it's not coming from a center point, but it would be an enlargement of 2. The scale factor would be a 2 to 1 or a 1 to 2 scale factor. So yes, those are similar. What about the 2 parallelograms? Are they similar? I see a scale factor of 2 again. If you double all these, you get the same. You get the twice as big on the sides. So are they similar? What has to happen for 2 figures to be similar? They have to have congruent angles. Do you see congruent angles? No. So definitely no. Angles not congruent. So that's a definite no there. Angles are not congruent. Now what about the last 2? Are those similar?
Yeah.
Okay, we can prove right now that they're congruent. Well, don't we have an S here? We have, what else we got here?
Angle.
We got an angle. Where? Down here? We got, and if these 2 are the same, what does that mean about these 2 angles?
They're the same.
So really we have an AAS or an AAS, right?
Yes.
So we could say they're congruent, so does that mean they're also similar? Or are they just congruent?
It's congruent and symmetrical.
Yes, they are congruent and similar. So what would the scale factor be in those two?
1. 1 to 1.
1 to 1 scale factor. You're right. So yes, you can be similar and congruent. So you would put yes, similar, and congruent. And that would be a scale factor of 1 to 1. Okay, so that has a scale factor of 1 to 1. So similar could be also congruent. Congruent figures can be similar because they have a 1 to 1 scale factor. Let's see. This is called a perpendicular bisector, if you remember correctly. And this is called an isosceles triangle from before, too. Okay, let's find the perimeters of these two figures. Okay, so what would the perimeter be for my little triangle? A 2 plus 3 plus 4. Not 10. Perimeter is 9, yes. Okay, so the little triangle, you got a perimeter equals 9. I should actually put big P for perimeter. And then the perimeter of your bigger triangle. You got 4 plus 6 is 10, plus 8 is 18. Okay, what was the scale factor of my two sides? It is a 1 to 2 scale factor. So if you double the small ones, you get the big ones. The scale factor is a 1 to 2 scale factor. So what do you notice about the perimeters, though? Do they have the same scale factor? So if if two figures are a 1 to 2 in their sides, the perimeters are also going to be 1 to 2. That's correct. That will always happen. Because how do you get a perimeter? Just add the sides. And if the sides are 1 to 2, the perimeters have to be 1 to 2. That doesn't work for area. Area is something totally different. But here's the little perimeter of similar polygons box for you. It says if two polygons are similar, the ratio of their perimeters is equal to the ratio of their corresponding sides. So if two triangles are similar, the perimeter ratio is the same as the side ratio. If you want to shorten it up, you can. But the perimeter ratio equals the side ratio. Two polygons are similar. Perimeter ratio is the same as the side ratio. And you can see it right in this picture over here. 1 to 2 scale factor. When you reduce 2/4, you get 1 to 2. When you reduce 9/18, you get 1 to 2. Same scale factor. Same scale factor when you have a perimeters to their sides. If the figures are already similar, the scale factor for the perimeters is the same as the scale factor to the sides. There's just one last slide here. A couple last quick things. Are you guys good to go? Okay, I can come back to it if you need me to at the end, but I'm going to move on. Jacob is making a model of the White House. Okay, it says the perimeter of the White House is 506 feet. Jacob will be using a scale factor of 5 feet to 1 inch. Do you see that right there? 5 feet to 1 inch. That looks like a ratio to me. Do I need to put the 5 on top, or could I put the 1 on the top if I wanted to? Correct, it doesn't matter as long as you stay consistent in both your ratios. So you could put 5 feet over 1 inch. Now they want to know how long will his perimeter be if the White House's perimeter is 506 feet. So what's going to go on top? 506, because that's my feet. And then on the bottom is you're going to have your x inches. So you can see you could still solve it for your finding your scale factor and then using your perimeters. It's the same ratio, it's the same kind of proportion. So you multiply 5 times x, you get 5x equals 506. And if you divide by 5, x should equal 101.2 inches. So it's a pretty good scale. It's a pretty good sized model. It's more than 8 feet around the model. So it's not like a really tiny model of the White House. It'd be pretty good size. And the last one is simply asking us for a scale factor. Now, it's assuming that these are similar, but let's prove that they're similar. We're going to look at each individual side. So to find the scale factor, we're going to look at each pair of corresponding sides. So what does the 3 match up to in the bigger triangle? 6. What does the 4 match up to in the bigger triangle? Good. So 4 and 8 are both the middle sides. And then the 5 matches up to 10. If these are similar, they will all reduce to the same ratio. And what will we call that ratio? Not what is the ratio. What would we call that ratio that they all reduce to? It's got 2 words. Start with an S. Scale factor. Yes, we would call that the scale factor. If they all reduce to the same thing. Do all of these reduce to the same thing? Yes, they do. What do they all reduce to? 1 to 2. That would be our scale factor. A 1/2 scale factor or 1 to 2 scale factor. So that's how a scale factor will work. You'll find out if they're similar, then you find the reduced ratio of the corresponding sides. That will be your scale factor. Okay, so you have a school net that corresponds to this notes.